Okay, so this lecture is over ring compounds again, but this time 6-membered rings, so just cyclohexane. And look at what does it look like in 3 dimensions? What's the structures of cyclohexane rings? So if cyclohexane, so I have the model here, if it was planar, then if you can see, so if it was planar, then all of the CH bonds are eclipsed with each other. So there's a lot of torsional strain there. So if it's planar, you have torsional strain. Which is destabilizing. So the molecule doesn't want to be planar. So what cyclohexane does, basically let's take one of these carbons and bend it up, and the opposite carbon and bend it down. So this carbon goes up and this carbon goes down, and it looks like that, which is what's called chair cyclohexane. And by making a chair, then you can see the hydrogens are no longer eclipsed with each other. Now they're all gouged to each other, so they're all staggered conformation. So they would be like that all the way around the ring. All of the CH bonds are now staggered with each other, and that's a much more stable conformation. So that would be chair cyclohexane. So if we try to draw that, so that's the chair, and then so each of these chairs has a hydrogen up, vertical, and then on the next carbon it would be down, and then the next carbon it would be up, and then down, and then up, and then down. And those are the vertical positions are called the axial position. And then each cyclohexane carbon then also has a hydrogen that's pseudo horizontal. So you can see that's not really horizontal. If this is perfectly vertical, this is kind of at an angle going down, but it's somewhat horizontal. And this one over here is somewhat horizontal. So this one's kind of going down, and that one's a little going up. So if we drew that as a Newman projection, then this carbon in the front is an upside down Y, and this carbon in the back is a Y. So they each have a horizontal position. And that's what's called the equatorial position. Okay, so the cyclohexane chair conformation, all bonds are staggered, so it's free of torsional strain, and the bond angles are about 111 degrees, which is almost the 109.5 degree for perfect tetrahedral carbon. So it's free of angle strain. So in general, cyclohexanes are very stable ring structures, and they're very common in organic chemistry. Okay, so if we have the cyclohexane ring structure, so cyclohexane constantly is doing what's called a ring flip. So let's take this carbon and bend it down, and this carbon and bend it up. So that's what's called a chair flip. And it does that several 100,000 times per second. So again, molecular motions are very fast. And so for cyclohexane, of course, the chair flips results in an equivalent structure, so there would be equal probability of both. Okay, so but what if it's not just cyclohexane? What if there's something attached to cyclohexane? So maybe it's something like methyl cyclohexane, or it could be a chlorine or a bromine, just anything attached, an ethyl group, an isopropyl group, doesn't matter. So then if it's a chair, so if we take the cyclohexane and we take off one of these and put something else there, so if we put a blue atom there, so I take my cyclohexane, I put it back flat, perfectly flat again. Well, not perfectly flat, but, and then if we take that and put it into a chair, so if I bend this carbon up and bend that carbon down, then you can see that that methyl group is in an axial position, right? It's vertical. So again, you got axial up, and then axial down, and then axial up, axial down, axial up, and axial down all the way around the ring. So that methyl group could be in an axial position, or if it did a chair flip. So whenever you do chair flip, anything that's axial goes equatorial, and anything that is equatorial goes axial. So everything swaps position. So you can see that here. If I take this carbon and bend it down, and then the back carbon bend it up, so I have the opposite chair, then you can see that now the blue atom is in equatorial position. So it's constantly going back and forth, so flipping back up. Now it's in an axial position again, flip it back down, now it's in an equatorial position again. Okay, so if we did the chair flip, then this is axial, and then it goes equatorial, and this is equatorial, and it would go axial, and every single thing on every single carbon around the ring, that's what would happen to it. Okay, so now these are not equivalent structures, because does the methyl group want to be axial, or does the methyl group want to be equatorial, or does it matter? So if we put it back axial, let me attach a couple other things to the ring so it's easier to see. So if we take the carbon that the blue atom is on and go 1, so that would be carbon 1. So this will be like 1 methyl cyclohexane. So carbon 1, 2, 3. So if I look at this hydrogen here, and carbon 1, 2, 3 the other way, this carbon here. So if this is in a chair, then this atom at carbon 1 is axial, and the atom up, and then atom 2 is down axial, and then 3 is up, and then 4 is down axial, and then 5 is up axial, and then 6 is down axial, right? Because axials alternate up, up, down, up, down, up, down. So if it's axial, then this methyl group is kind of close in space to this hydrogen, 3 carbons away, and this hydrogen 3 carbons away the opposite direction. So you can see then they're eclipsed. So that blue atom is eclipsed with this hydrogen. That's in the 3rd position, and this one that's in the 5th position, you can see that it's also eclipsed with that one. So that's what's called a 1, 3. So if we draw those, that would be, whoa. So if we draw those hydrogens in, that there would be a steric interaction there and a steric interaction there. That's what's called a 1, 3 diaxial interaction, where those atoms are eclipsed. So that's unstable. Where if it does a chair flip, and that goes there and that goes there, then now the methyl group is in an equatorial position, and you can see that it's staggered with respect to these 2 hydrogens, and with respect to these 2, it would be staggered with respect to those as well. So now it has all staggered interactions. Dang it. Undo. So the basic point is any group on cyclohexane prefers to be equatorial instead of axial. And the bigger the group is, the more it prefers to be equatorial. So simply it's got more space if it's in an equatorial position, because if it's in an axial position, then these 1, 3 diaxial interactions destabilize it. So for methyl cyclohexane, both of these axial and equatorial conformations exist. So these are conformational isomers, because how do we go from one to the other? we rotate. We rotate around these bonds and we rotate around these bonds. And anytime you generate different molecules just by rotating around bonds, those are conformational isomers, not constitutional isomers. But one is preferred over the other. In this case, the molecule exists about 95% of the time with the methyl group in the equatorial position, and only about 5% of the time with it in the axial position. And then the bigger that group is, if this was a tert-butyl group, which is significantly bigger, then it's about 99.99% of the time in the equatorial position, and only about 0.01% of any of the molecules at any one time would have the tert-butyl in the axial position. Okay, so what if you have two things on a cyclohexane ring? So let's say we have two chlorines. Then there are two possible isomers, right? Those are the same. So now what kind of isomers are these? We've looked at three kinds. Are they constitutional isomers, or aka structural isomers, or are they conformational isomers, or are they stereo isomers? And the answer is they are stereoisomers, right? So if we take this, put two things on the ring, so that would be, so both chlorines are on top of the ring, so this would be like they're both on solid wedges, or they could both be on bottom, and then they would both be on dashed wedges. And if you wanted to make the other one, right, we can't get to the other one by rotating around bonds. You have to break bonds and remake bonds. So they're not conformational isomers because you can't rotate to get to the other one. You have to break bonds. And they're not constitutional isomers, structural isomers, because the atom attachment is the same. It's carbon with a chlorine, carbon with a chlorine. Doesn't matter if they're cis or trans. They differ spatially, so they would be stereoisomers. Okay, so if we take this one, so this one would of course be cis, and this one would be trans. Right, so they're both on top, or if they were both on bottom, that's cis. One's on top, one's on bottom. One's on solid wedge, one's on dash wedge, so that means they're trans. Okay, so but they're not planar. They exist in a chair conformation. So if we take the trans and put it in, we'll start with cis. Let's start with trans since we have it built. If we start with trans and put that in a chair, if we bend this up and bend that down, then the two blue atoms would be axial or equatorial. Well, they're both somewhat equatorial, or somewhat horizontal, so they would be both equatorial. So if we started with trans, and put it in a chair, let's see, let's do this. So I'm going to basically take this carbon and bend it down, and I'm going to take the back carbon and bend it up. So if this carbon goes down, then that chlorine would go equatorial, and that hydrogen axial. And this hydrogen, so that hydrogen would go axial, and this chlorine would go equatorial. So they would be 1, 2, E, E, and that is trans. And then if we do a chair flip, so if I flip this up, so let's see, yeah, that up, what do we got here? That's my chair. So I need to flip this down and that carbon up. And then if we do that chair, then you can see now both of the blue atoms are vertical. So now they're both axial. So if we do the chair flip, then we get that confirmation where they're both axial. So 1,2AA is also trans. And if we started with the cis isomer instead, and if we put that into a chair, so let's flatten it back out, make the cis isomer. I'm going to take this carbon and bend it down, and the back one bend it up, and then you can see if I put that into a chair, then this chlorine is axial and this one is equatorial. And if I do a chair flip, so if I flip that up and then flip this down, then now this one is axial and that one is equatorial. So if it's cis 1, 2, then one group is always axial and one group is always equatorial. So cis 1, 2, then one group is axial, one is equatorial. And if we do the chair flip, then this is axial, it would go equatorial, and this is equatorial, and it would become axial in the process. Okay, so if two groups are cis to each other on a cyclohexane ring, when it adopts a chair, one group will always be axial and one will be equatorial. And so there would be a 50-50 probability of these two. But how about the trans isomer? Which one? So if it's trans, you could either have both equatorial or both axial. So which would be more preferential would be the one where they're both equatorial. So this would be the most stable. So if I gave you trans 1,2-dichlorocyclohexane and asked you to draw the most stable conformation, you would have to draw it as a chair, and you would have to recognize both of the chlorines need to be equatorial. If I gave you cis 1, 2, so this is cis 1, 2 dichloro cyclohexane, and I ask you to draw the most stable conformation, well, one of the chlorines has to be axial and one of the chlorines has to be equatorial. Okay, what if it was a 1,3 isomer instead? So it could be cis, or it could be trans. And then, of course, the other possibility would be what if they're 1,4 with respect to each other. So that would be cis 1,4. And that would be trans 1,4. The 1,3 isomer. And I make it flat. So now it's flat, so everything's eclipsed. And then I put it into a chair. Then you can see that both the blue atoms are vertical, so both axial. So if it's cis 1,3, they're both either axial, and then of course if you do a chair flip, everything axial has to go equatorial, so they can then either be both equatorial, both horizontal as well. And the one that's going to be more stable, of course, is the EE. So you can see it's exactly opposite of 1,2. 1,2 cis is AE, but 1,3 cis is AA or EE, which is what 1,2 was. 1,2 trans is AA or EE. So 1,2 is exactly opposite of 1,3. So if we had the trans isomer instead, so now that's trans because one of the chlorines is on top of the ring and one is on bottom. And if we put that in a chair, then that one's going axial and this one's going equatorial. Right? And if we did a chair flip, then this one's going to go equatorial and then this one is going to go axial. So if it's a trans 1, 3, then one group has to be axial, one group has to be equatorial, which is exactly opposite of 1, 2. So can you predict what 1, 4 would be then? So if we went from 1, 3 1, 2 substitution to 1, 3 substitution, that changed everything. And then if we go from 1, 3 to 1, 4, it's going to change it back. So cis 1, 4 is going to be axial equatorial or equatorial axial. And if you did trans, they're both going to be axial or they're both going to be equatorial. So we'll just do one of these with the model so that you can see that. Okay, so now they're 1, 4 with respect to each other, right? This is carbon 1, 2, 3, 4, and that would be the trans isomer. So when I put this into a chair, they should both be axial or they'll both be equatorial. So if I flip this one up and that one down to a chair, now they're both axial, right? They're both vertical. And if I go the opposite direction, if I flip this one down and that one up, then now they're both horizontal. So they're both equatorial. So in terms of stability, that would be the most stable. Okay, so another thing you have to be able to do. So if I just give you a drawing of a chair. So let's say I give you this. Let's see. And let's see, okay. Okay, so each of these rings that I just drew, are they cis or are they trans? So let's name them. So this would be carbon 1, 2, 3, or you could have started at the other carbon, it would give you the same. So this would be a 1, 3 dibromo cyclohexane. But is it cis or trans? So you can see that this is axial and this is equatorial. So there's two ways to do this. You could memorize it, which is the hard way. So if it's 1, 3, and one group is axial, one group is equatorial, that's trans. Or the easier way is to say, okay, if you look at this, this is on top of H, whereas this bromine is on bottom of H. So that's opposite. Opposite is trans. So that would be trans 1, 3 dibromo cyclohexane. And for this one, so you can see that the ethyl is on top of hydrogen, and here ethyl is on bottom of hydrogen. So one's on top, one's on bottom, that's trans. So this would be trans 1, 4 diethyl cyclo. So don't forget the cyclo part. Students forget the cyclo part all the time. Okay, how about for this molecule? Is it cis or trans? So this group, so first of all, what is that group? If you recognize that group, that is a tert butyl, right? It's 4 carbons, and you got 1-2 carbon chain off the parent cyclohexane, and then 2 methyls on the front carbon. That's tert butyl. So this is on bottom of hydrogen, right? It's on the bottom of that hydrogen, and chlorine is on top of that hydrogen. So this is another example of a trans isomer. So this will be trans, and then if you're naming this, where would you start numbering from? So is it 1 chloro 2 tert butyl, or is it 1 tert butyl 2 chloro? Well, you're alphabetized tert butyl based on B, so it comes first in the alphabet, so it's going to be number 1, and chlorine is going to be number 2. So 1 tert butyl 2 chloro cyclohexane. Okay, so one more. Let's go the opposite way. Let's draw cis 1, comma 2 dipropyl cyclohexane. So if you're going to draw cis, so we could draw it one of 2 ways. We could draw this. We could just use the dashed wedge structure. So since cis, they both have to be on a solid wedge or both have to be on a dashed wedge. So you could have drawn that, or and of course you don't have to draw CH2, CH2, CH3 out. You can use line formula. So you could draw it like that. So where if you recognize, so that's a carbon. Oh, come on. Oh no. What did I do? How do I get rid of that? Thank you. So that is a carbon right there, right? Because that's a break in the line. So that's carbon 1. And that's a carbon. And that's a carbon. So that would be a propyl chain. So you can use line formulas or you can write it out like that. Doesn't matter. So both of those are cis. But if I ask you in the most stable conformation, then you would have to draw it as a chair. So draw a chair, axial up and an axial down on the 2 adjacent carbons, and then both have a horizontal position. So if it has to be cis, so let's see, let's put hydrogen there and a propyl here. So this is below H. So if it has to be cis, then the next one has to be below H as well. So that means, so they're both below H, so they're cis to each other. Or one more. Draw 1, 3, let's draw cis, 1, 3 difluoro cyclohexane. So probably what I would do on a test is I would give you a template like this and just ask you to fill in where things are at. In the most stable conformation, which means if I told you most stable conformation, that means you can't draw it like this, because most stable conformation of cyclohexane is chair, so you have to draw it in chair form. So let's see, so we can put one of the fluorines here, and then that's carbon 1, 2, 3, the other goes here. So if they're cis, so this is below H, so the next one has to be below H. So we would draw it there. Of course, you could have drew the opposite. You could have put them both above H, and that would be cis, right? So this is above H, and this is above H. So they're same, that means they're cis. So these are both cis, but I ask you if the most stable conformation that's not the most stable, right? This is the most stable because they're both equatorial. Whereas here they're both axial, and that is unstable. Okay, so that's it. So hopefully that made sense.